This chapter is the shear design chapter in concrete design. This, by the end of this chapter, you'll be able to use the simplified method to design beams for shear or check the adequacy of beams against shear stresses. What we learned from before is that due to loading on different beams, such loads would induce stresses, internal stresses like moments and shears. And once we get the value of the internal moment and shear within the beam, we should be able to design the beam or the member to resist the moment as we described in the previous chapters. And then in this chapter, we're going to go over the shear design. Now, looking at a simply supported beam on two columns, as in the figure here, from analysis of structures or structural analysis courses, you remember that where the shear is maximum is towards the support, right? These could be different by different loading configurations, but then what we're looking at here is for a simply supported beam, the maximum shear happens very close to the support. Now, let's think about the failure. Why do we think about the failure? Because our limit state is always concerned with what happens at failure. So basically what I'm going to be working on is finding phi Vn. And the Vn is the shear at failure. It's the nominal shear load. It's the load that causes this section to fail. How does it fail? It fails something that looks like this. On a 45 degrees angle of a crack, or something close to the 45 degrees. They say it's between 25 to 65 degrees an angle, talking about this angle. And the reason for this is very simple. If we take one of those simple small elements, as we will describe now, here, if I take an element that is pretty much was here in this place, the shear stresses look something like this. Over here and over here. This is how the shear stress look like. I'm taking that out here, and due to equilibrium, this piece of concrete or of the element will not rotate. And the reason why it's not going to rotate is that there is a coupling force that resists this rotation. Where does it come from? Where those guys came from is that because there are surrounding elements above and below this element that will not allow it to rotate. So the resultant of these two forces will end up going this way, and the resultant of these two forces will end up going that way, and this will induce a crack that goes on about a 45 degrees. They say this angle over here is around 45 degrees. In more complicated ways, they talk about an angle between 25 and 65 degrees between the horizontal and the shear crack. So we'll take it for the simplicity, we'll take it as 45 degrees. Now you will come and say, what if I don't have elements or concrete above or below? For example, like the edge here and the edge there. I would say get back to solid mechanics, and you will remember that the shear stresses looked something like this for such a member, which means the actual stress at the top and the bottom equals to 0, right? And the reason for this is that because you don't have elements above or below that can resist such rotation. So the stresses end up being 0, and the maximum stress is at the middle because you have the most amount of concrete above and below the middle. Now it says that shear failure is brittle. Remember this very important fact. Shear cracks are diagonal. This is one of the things that inspectors always look at because shear cracks are very critical. These are such behaviors that we don't like in structural engineers, and we avoid as much as we can because brittle failure is a sudden failure. It does not give any warnings. Now, how do we design shear? Is we simply get the demand from our forces, which is Vu, and then we compare it to our capacity. Where does the capacity come from? The capacity comes from my phi multiplied by my nominal shear strength. This is the at failure shear load. Well, this here is my strength reduction factor, and for shear, it is always equal to 0.75. Now you will see, or you will notice, that this is smaller than what we had for tension controlled members, simply because shear is a brittle behavior, or shear failure is a brittle failure that is not very favorable. So we had to reduce, or the code had to reduce this phi to 0.75. Now Vn, this is the failure load. Where does it come from for our beams? It comes from two parts. The first part is the concrete itself, which means when are you going to break that concrete before it even gets into the steel? So that means my section itself, it resists the shear as far as the concrete section, right? And that resistance, in addition to the steel, will give me the final resistance. So the concrete nominal shear strength is Vc, and then the steel shear strength, which comes from mainly from my stirrups. So it comes from those stirrups. I have a stirrup over here that resists shear. So this is the one that gives me Vs. And then I have the concrete section itself gives me the Vc. How do I calculate Vc? For the simpler form of it, because there are more complicated equations in the code, I just take it equals to 0.75 square root of f prime c b web, which is the width of the beam, times d, which is the depth of the section. So it goes down to only to the steel bars, right? We don't consider the concrete cover as part of the resistance. Okay, so this here is my b web times d times 0.17 f prime c. Remember that units are very important. F prime c here must be in megapascal, b web is millimeters, and d is millimeters. We cannot change the units here because the 0.75 is a coefficient that is based off these units. For the steel resistance, or the contribution from the steel, as we agreed, what really resists that 45-degree crack from happening is the presence of those steel bars. And those steel bars are, we call the stirrups. Those stirrups work with me as, if you see looking at the crack like this crack runs through a number of stirrups. So we're going to get here some stirrups. Here's one stirrup, say two stirrups, three stirrups, and so forth. Here are, for example, 4 stirrups. I'm running through 4 stirrups. If I consider the distance, the spacing between each stirrup and the next stirrup is S, and I consider this to be my D over here, then the number of stirrups that will be involved in this crack will be equal to D divided by S. Why is this? Because simply, if I consider this as a 45 degrees, getting into the black, this is a 45 degrees, right? Then if this is D, then this is also D. Then the number of stirrups here is 1, 2, 3, 4 that will be involved in the resistance of this shear crack will be equal to the distance D divided by the spacing S. So this here is the number of stirrups, N. Okay, let's look from this side. I'm going to look now from this side. Every stirrup, as this crack runs through, so I'm looking at the stirrup itself. Here's my stirrup. It will have to break how many legs within the stirrup. So I have to look how many legs do I have. So I'm looking at the legs, and the number of legs, so the number of legs, in this case it is 2, right? Because I have one over here and one over here. So this is a 2-leg stirrup. the number of legs multiplied by my area stirrup is the area of steel for the shear. Remember this very important fact. So now for every stirrup I'm running through, every one of those guys, I'm going to run through 2 legs. I'm going to have to break these 2 legs before my shear failure happens. So my AV will be equal to the number of legs multiplied by the area of the stirrup. Not the AS of the longitudinal. It's the area stirrup reinforcement. Okay, so if it is a single closed stirrup, it will be 2 legs, 2 times area of the bar. If I have a section that has more than this, for example, I have such big sections that happens a lot with bridge caps, those big bridge elements, you would see a stirrup that looks like this. There's a lot of free bars that come inside this, right? And then imagine that I will have more stirrups inside. So I have another stirrup here, and then another stirrup here, right? In this case, I will count how many legs I have. There's 1, 2, 3, 4, 5, 6 legs. So now I consider this as 6 times area of the bar, whatever the area of the bar is. This will give me my AV. Very important that you look, how do we estimate AV is through multiplying the number of legs times the area of the bar of the stirrup. And so now, getting back to the equation, what is VS? Simply my VS will be my AS, which is AV in this case, times F yield for the transverse reinforcement, we call it F yield T or FYT, times the number of stirrups, which is basically D over S. So this ends up being our final equation. AV F yield times N or times D over S. Times N or times D over S. Because that gives us right away how many stirrups will be involved in this shear crack. Now the stirrup detailing for a closed hoop, and it's a preferred option, especially for high seismic, high wind areas where beams will involve a lot of back and forth loading. This here is how a closed hoop look like. Normally here in the Middle East and in a lot of places, they don't prefer to close it this way. They would prefer it to be closed like this, which is also another good option, right? So this could also be considered a closed hoop, but for seismic reasons, they will tell you that a 135 degree hook is needed at the end of each stirrup when they close it. Now these are normal other shapes. Now this is an open one, another open one. But generally speaking, looking at this one here, you have 4 legs, right? This is not a permitted way to do stirrups for bridge beams or eye girders, especially that when you get such a girder, what will happen is the tension from this side and the tension from this side will end up in a resultant force this way, and this can spall out your concrete cover. So the best way to do this is, instead of having it this way, is you actually would run your stirrup coming from the web all the way, and then you would run another stirrup coming this way. So that is a detail that you will not have such a force. This will not happen, and you would protect your concrete cover. Over here are other ways to do stirrups, and in the code it tells you that there has to be a lap if you're having a really congested beam that you cannot run the whole cage as is inside. You can do the U shape of the lower one, and then another U shape, inverted U shape for the top one, but you have to make sure that there is some lap between them that is equal to 1.3 LD at least. Other cases is when you run a cross tie. This piece here, we call it a cross tie, on top of an open stirrup. This is also another permitted way for a two-piece closed stirrup. And normally we alternate those hooks. So the 135 and the 90-degree hook are alternated from one stirrup to another. Other ways for hooks with or standard hooked stirrup on beams are those ways. Again, those are not permitted in high seismic areas, but normally are permitted for simple structures in regular zones that doesn't require much of important detail. Now, the design of flexural shear in beams goes as getting your VU, basically comes from your shear force diagram where the maximum VU is, and then computing once I know the dimensions of my beam, I can simply compute my VC, and then my phi VC becomes 0.75 times VC, and this is the contribution of my concrete to the strength of the beam. Now, my next step is to figure out, do I really need stirrups or not? Like, imagine that I have a very, very high phi VC. If my concrete by itself can resist my VU, do I really need to put stirrups? Practically speaking, yes. You need to put stirrups, and you need to put, because you have to hold your reinforcement, your longitudinal reinforcement that will resist the flexure. But in terms of need of these stirrups to resist your shear, it depends on how much of a value of phi VC compared to VU. So simply, it says that if your phi VC is really, really high, that is more than double the VU, then there's no need for shear reinforcement. So if the VU is less than or equal half of the phi VC, there's no need for shear reinforcement. And then if the VU is just less than phi VC, then we just use the minimum stirrups or the minimum required stirrups by ACI. And in this case, you just pick up a value for your stirrup bar and then set up your spacing to be the smallest of those four values, right? And then place your first stirrups at S/2 from the face of the support. Let's take a quick example on this. Imagine that my V ultimate, this is the applied shear, was, for example, 40 kilonewton. I calculated my phi VC, and I found it equal to 100 kilonewton. That means only the concrete can resist more than double the applied shear. Now I have the applied shear is 40, I can resist 100. So I have more than double the applied shear. In this case, what's going to happen is, I'm going to say I'm in case 1 here. I'm going to call this as case 1, where I don't really need any shear reinforcement. I don't need any stirrups. If you're going to use stirrups, you're just going to use it for detailing purposes to hold your cage in place. Now imagine the second scenario. I have an applied shear equals to 80 kilonewtons. Well, I have the same section, so it's 100. Now my 100 is more than the applied shear. Then in this case, the code tells you that you have to use a minimum amount of stirrups. Now that minimum amount of stirrups, you could simply say that I'm going to pick up one of those small rebars, for example, phi 8 or phi 10, and then set up my spacing accordingly. And in this case, my spacing is taken from those four values, and those I picked the smallest of them because that's the safest. So I pick up my S maximum to be the smallest of these ones, and then put my very first stirrup at S/2 from the face of the support. Now, what if my VU is larger than, now that's a good design, now my VU is larger than my phi VC. This is a really good design. Why? Because you're really using your stirrups. Now, your stirrups are not just there for sitting there doing nothing. They're really being part of your design. This is a more economic design. And in this case, I will have to calculate my VS. How do I calculate my VS? I will simply say that my VU will be replacing what? Phi Vn. And this will be equal to phi times Vs plus Vc. Vc plus Vs. And then pull this guy out on one side, you end up with this equation. So I have a Vs equals to V ultimate minus phi Vc divided by phi, right? Now in this case, once I get Vs, it's important to check how much of a value of Vs do I need. The code tells you that if you're really going to use your stirrups for so much stresses, meaning that you have a very small section, in this case your Vs is bigger than 0.66 square root of f prime c b web d, this will not work. You cannot use such a design. You cannot design it to have a very, very high Vs, really, really high Vs, and really low Vc. This is not permitted by ACI. There has to be some balance. And in this case, it would be good to have it either smaller than 0.33 square root of f prime c b web d, or in between 0.33 and 0.66 that value. The only difference between them is that the criteria for the spacing in these two parts will be d over 4 and 300 millimeters instead of d over 2 and 600 millimeters. So get this value, the Vs that you got, and then compare it to these two numbers, 0.33 and 0.66 square root of f prime c b web w. Those four criteria is the same criteria as the previous slide, 1, 2, 3, 4, except that the difference between here and there is that d over 2, 600, d over 4, 300. But the very first one we're looking at here is actually the Vs calculated value. How do we calculate Vs? If I'm given a section, Vs equals to a V F yield of the transverse D divided by S. So I simply got the S out, got the Vc down to get this S. So what is happening here is that I will have to assume, before I get into this, I'll have to assume some rebar, maybe phi 8, maybe phi 10, maybe phi 12, depending on the size of the section. I will have to assume a number of legs. So I have to say, for example, I'm going to start with 2 legs. Those are my 2 legs that are working for me. Here's one leg, here's another leg. And then find my AV, plug it in here, and then get my S. So it's kind of a trade-off. You'll have to assume something and then work your way through to get other values. Now those other values get to have no sense. They're too small or too big. You change and update your design accordingly. Let's get into an example. Here, example 7.1 tells you to calculate the spacing of number 10 stirrups. So already here is telling you use number 10. That's a nice thing as a good starting point. I have my AS right away will be equal to 71 millimeter squared. This is the area of the bar for number 10 stirrup. At the critical section, all the simply supported T-beam shown below, it's a T-beam, which will not affect our shear design. In the figure, elevation and cross section. Now, this beam supports a uniformly distributed surface dead load equals to 20, including its own weight. When I say including its own weight, that means they've already calculated the own weight and it is part of the 20. You don't need to calculate the own weight. And a uniformly distributed surface life load of 24. So I have a dead equals 20, a life equals 24, so definitely have to combine these two. The concrete compressive strength is 25 and the yield strength is 300 megapascal. Concrete is normal weight concrete. Now, first step is to get the value of VU. I have to get WU, 1.2, 1.6, that gives 62. And then RA, that's the reaction in both directions, equals RB equals WL over 2 equals 312 kilonewtons. Now I want it at the face of the support. Why would I need it at the face of the support? Is that simply right above the support, your span didn't start. So it doesn't make sense that I start my calculations. If I placed my representation of my support in the middle part of the support, I got my shear, it looks like this. Now the value of the shear here is the actual starting value of the shear. This value of the shear does not really exist. It does not really exist because I had to represent that support by a pin right in the middle of the support. So I have to calculate it at the face of the support, right? If I don't do this, I'm going to be over designing my beam. I'm going to have to design for a higher VU than the actual VU that is subjected to it. And by the way, there's even more than this, that in the code it tells you that you're okay going D away from the face of the support to calculate your VU. But I wouldn't do this now. I have to be competent enough to do this because in some cases that does not apply. In some cases that does not apply. So let's just skip this for now. A little bit more expert of analysis and dealing with the structures would be able to figure out where or when to go D away from the support. And we'll, for now, for just the simple ways of calculating things, we're just going to do it at the face of the support. So how do I get it at the face of the support? I can simply say, I'm going to take half of a support. My full support was 0.3 meters, right? So half of the support is 0.15 meters. And in this case, I just multiply that times the load applied to get down from this value to this value. So I simply say 312 minus that distance times 62.4, which is my W, equals 302. This is my VU max that I should be designing the beam for. And then my next step is, let's check if that section can take it or not. VC will be 0.17 square root of F prime C D times B, or B times D. That gives us 155 kilonewtons. Now, applied 302, resisting of just concrete 155. Do I need steel? Yes, definitely I do need steel stirrups, and they will be working with me. Now what do I compare? Normally I multiply this by phi, so that's multiplied by 0.75, that gives 116. So out of the 302, my concrete can take 116. The remaining shall go to the steel. What is the remaining? I have to calculate Vs. That's going to be the 302 minus the 116 divided by 0.65, because this is already multiplied by 0.65. Then the amount of steel need to resist 248 kilonewtons just by the stirrups, right? It's a very important number. Now, my first choice was given in the example as the number 10 bars. Definitely I needed 2 legs, that's a minimum. So that means my 2 legs gives me 2 times 71, that is 142 millimeters of reinforcement per stirrup. And then let's check the amount of steel that came out, or the amount of resistance for the strength needed by the steel is 248. Let's now check it against the 0.33 and the 0.66. Now the 0.33 square root of F prime CBD, that gives me 302. I am less than this. That means I'm in the first column of the 3 columns in the slide figuring out how to calculate this. And the first column simply tells you that you need to pick the smallest value out of these 4 values, right? Out of these 5 values. right? The first one is the calculation, and then you compare it to those 4 values. Normally I say 4 values because those 4 values are just minimum. While this is what is really needed by the strength. What is really needed by the strength is AV F yield D divided by VS. So by the strength I need 105, but then I have, for detailing purposes, I have to check it against all these 4 values. As I said, in the first column it's D over 2 and 600. If it was bigger than the 0.33 but smaller than the 0.66, then those 2 values are changed to D over 4 and 300. Now I picked up 105. In this case, because it's an S, it's a spacing, then I have to drop down this to the nearest 5 centimeters, which means I pick up 10 centimeters, 100 millimeters. The first stirrup in the detailing comes in as half a stirrup size. The first one, by the detailing of the code, needs to be half a distance, half an S away from the face of the support to ensure that you have it close enough so when the crack starts to propagate, it right away hits a stirrup. It doesn't have to wait all the way until S is over. Just for detailing purposes. Example 7.2, the figure below in an elevation and a cross section shows a continuous beam. So this is like a continuous beam that looks like this, and this is just the first span of that continuous beam with a factored load W ultimate equals 99.2 kilonewton per meter. That accounts for the floor loading, the beam on weight as well. And the concrete compressive strength F prime C equals 25, and F yield for the stirrups equals 300. The concrete is normal weight. Design the vertical stirrup at the critical section using number 10 bars. The main reinforcement of the beam are number 22 in one layer, and this is for the purposes of calculating year D. Assume that all conditions of ACI alternate analysis method are satisfied. What are the analysis or alternate analysis method? It's a method that we will go over in the next chapter when we go to the one-way slab that can simply calculate the forces for you in an indeterminate structure if it satisfies some condition. And we'll see how this applies here. The ultimate shear here, based off the alternate analysis method, at the beginning of the span will be WL over 2, and at the end of the span will be 1.15 WL over 2. And then this one dictates because it's higher, so we're going to use this one. This is what simply your alternate analysis method tells you. And then you multiply those numbers divided by 2. That gives 513.4 kilonewtons. Then calculating your D will be, since I have a stirrup size 510 and I have a main bar 522, I simply say 900 minus the concrete cover minus 10 minus 22 over 2. That gives me 839 millimeters. Those are assumption, and this was given in the example. Calculating my VC, that's the strength based off the concrete, will be equal to 0.17 square root of F prime C times B times D. That gives me 285.3 times phi, which is 0.75, that gives 214. I think these are very simple steps. And then my ultimate shear compared to the phi VC is much higher. So in this case, I need some stirrups. How do I need the stirrups? In this case, my stirrups will be based off one of those 4 criteria for the spacing. But the very first one would be based on calculating your strength. The steel strength will be 399. So I just subtracted my concrete strength from the applied load divided by 0.75. That gives me 400, about 400. That's 399.2. I have to compare this to the 0.33 square root of F prime C BW D. Since this was greater than the VC, then the first column applies, and you're simply having a D over 2 or 600 in the last 2 columns, and then I'm comparing the criteria from the strength to the criteria from the detailing, picked up the least one, which is the 90. Now I will have to put those at 9 centimeters distance. The distance here between each one and the next one is 9 centimeters, while the first one will be at 4.5 centimeters, right? It's important to understand that those are not very practical numbers. Nobody really puts spacings to be at 9 centimeters. So if you're having the chance to revisit your fee, then you have to go back and do it. Which means instead of using a number or a phi 10, I can use a phi 12 and then recheck. I might get a better number than this. It could go, for example, to a 10 centimeters or 12 and a half. A 12 and a half is also a good number, or 15 centimeters spacing between the stirrups. Why did I say 12 and a half? Because simply you can put every 25 you put 2 stirrups. So they can easily do this on the site. That's it for this chapter. I hope this is clear enough how we calculate the strength of a beam, how we find the spacing, and how we design beams for shear. Thank you for watching.